Hello everyone, I'm Uma Shravanti Gullinki, studying MTech in Computer Aided Structural Engineering from Mahindra University. Today, I'm going to talk about my course project in Infrastructure Health Monitoring. The project title is Experimental Investigation on Deck Damage Identification and Retrofitting Performance in a Cable Stayed Bridge using Piezoelectric Sensors.
This project is done under the esteemed guidance of Dr. Visalakshi Talakokula and with the support of Mr. Ramesh Komasa. This is the outline of the presentation. I'll begin with an introduction, followed by objectives, methodology, and experimental details. Later, we'll go into results from EMI and RMSD techniques and finally conclude the key insights. Modern cable-stayed bridges like those designed by Calatrava offer a balance between elegance and structural efficiency. However, conventional inspection methods are labor-intensive and may fail to detect hidden internal issues. This study explores the use of piezoelectric sensors which respond to mechanical strain by generating electrical signals for real-time damage detection. With advanced signal analysis, we aim for early, accurate, and predictive maintenance of infrastructure. Our objectives are to assess the feasibility of electromechanical impedance techniques using bonded piezoelectric sensors for bridge deck health monitoring. We aim to distinguish between healthy, damaged, and repaired states. Use impedance shifts as an indicators of damage. Validate the method for real-world applications including machine learning and wireless integration for scalable SHN systems. We begin by designing a scale model of cable-stayed bridge using CAD. 5 PZT sensors were surface bonded on the deck. Baseline impedance values were measured, followed by damage simulation by drilling holes at controlled intervals. Post-retrofit values were again captured. All sensor data were processed using MATLAB for EMI and RMSD analysis. This slide shows the geometry of fabricated steel bridge. Proper scaling ensures realistic dynamic behavior for meaningful sensor data. Here is the dimension bridge model. Key materials include MS sheet 3 mm for deck slab, high tension steel wires for cable simulation, epoxy adhesive for sensor bonding, U-bolt clamps to regulate cable tension, and drilling machine to install holes. 5 piezoelectric sensors were installed at 100 mm intervals along high strain zones near pylons, midspan, and anchorages. This ensured optimal sensitivity and uniform coverage across the deck. We used an LCR meter to capture impedance values at each phase, healthy state, after incremental drilling, and post-retrofitting. This allowed us to track dynamic changes in structural behavior quantitatively. Using the EMI technique, the impedance response of each sensor was captured between undamaged and damaged states. Visible shifts in conductance signatures indicate structural disturbance, making it a powerful qualitative tool. To quantify the damage, we use the root mean square deviation technique. This compares the conductance signature before and after damage. A higher RMSD value corresponds to greater deviation and thus more severe damage. Here, we see the conductance profile from sensor 1. Damage slightly shifts the resonance peaks, suggesting the low sensitivity or minimal structural degradation at this point. This may be because the location is either structurally redundant or far from the drilled region. Sensor 2 shows more obvious signal deviation compared to sensor 1. There is a clear rightward shift and flattening of peaks, indicating localized stiffness reduction and better sensor responsiveness. Sensor 3 provides one of the strongest deviations. The conductance curve visibly distorts, confirming that this region of the deck absorbed a larger portion of the structural disturbance from the whole. Another critical response comes from the sensor 4. The distinct separation between the healthy and damaged curves indicates that the sensor 4 is in a dynamically sensitive zone, possibly close to a core or its stress concentration. Sensor 5 shows significant deviation, particularly in mid-frequency ranges. This confirms both damage detection and capability and proper sensor placement strategy near anchorage or pylon regions. We have considered only third level of induced damage, referred to as damage 3. This provides a consistent and severe benchmark for evaluating sensor performance. The composite plot in this slide shows conductance responses from all 5 sensors responses in 3 stages: healthy, damaged, and retrofitted. You can observe partial conductance recovery after bolted repair. Retrofitting is most effective in sensors 1, 4, and 5. This confirms EMI capability not just for damage detection but also for monitoring repair performance. These slides zoom in the connectance behavior of each sensor after damage T and post-retrofit. All sensors showed partial recovery, confirming that the retrofitting was structurally beneficial. The curves still deviate from the original healthy state, suggesting restoration of the stiffness in the deck. These results support the RMSD metrics and demonstrate that EMI sensing is effective for both damage diagnosis and post-repair verification. To summarize, all 5 sensors successfully detected damage. Sensors 3, 4 and 5 were more sensitive. RMSD values provided quantitative correlation with damage severity. Post-retrofit data confirmed partial recovery. This method is promising for real-time and non-invasive structural health monitoring in bridges, tunnels and even aerospace. Future enhancements may include wireless sensing, machine learning and environmental calibration for robust deployment.
If you find this video informative, please do share. Thank you.